All right, so hello everyone. We are live, and so we just started our community talks. And right now we are having Hubert here today, and so he's going to talk about FairPAN makes networks fair again. So, Hubert, stage is yours.
Thank you. So, good evening from me. I'm Hubert Ruczyński, and this talk is an effect of an amazing opportunity which I've grabbed during this summer. For 2 months, I've gained my first scientific experience during MI2 Data Lab internship, where I could work along much more experienced researchers, and I'm really grateful for that possibility. Thanks to the people like my mentor, Jacob Wisniewski, I've managed to generate enough will to go out of my comfort zone and participate in this project. As I've mentioned before, during the summer, I've become the part of MI2 Data Lab, and that was my first work and scientific experience. I've also become an R package developer, and I study engineering and data analysis at the Warsaw University of Technology, where I'm on 5th semester of engineer's degree. Now I'd like to present you to the outline of this talk. At the very beginning, I'll make a short abstract-like introduction to this project. Later, I'm going to talk about two important subjects which you have to be familiar with before introducing to FairPAN. The first one is the concept of fairness, followed by the simple example of it. And the second one is about GANs and the introduction to them. And after that, I'll talk about how FairPAN works and why it is so good. I'm also going to prove that point by performance visualization. In the end, I'll talk a bit about FairPAN package and its workflow. So now, without any further ado, let's get to the main topic. The main topic of our study was the implementation and further research in the area of obtaining fair tabulate data classifiers with the usage of neural networks. To achieve such results, we modify the idea of GANs by swapping the generator with the classifier and adapting the adversarial to recognize the label of a sensitive value. This way, FairPAN, which stands for Fair Predictive Adversarial Network, should bring us much fairer predictions. As a result, we present a mitigation technique suitable for neural networks and explore this field even more. At the beginning, I'd like to introduce you to the concept of fairness. Consider the idea of the algorithm that has to predict whether giving credit to a person is risky or not. It is learning on real data of given credits, for example, German credit data, which were historically biased against females. In this case, the model learns this bias, which is not only included in the simple sex variable, but also hidden inside other variables. So removing this feature doesn't make the model fair. As a result, the classifier is more reluctant to give credits to women, even if every other condition is similar to the ones of men. Now, let's imagine that we are the director of the bank which uses this model. Personally, we are fully behind the equal treatment of men and women. But on the other hand, we have a biased model and we don't even know about it. In such situations, fairness proves that it is a really important thing and a part of science. The concept of fairness is sometimes really foggy, because we can't always say if some variable leads to the bias of the model, or is it just a good predictor. So I'd like to introduce you to my intuition behind it. Personally perceive fairness more like a tool to make your models suit to your personal beliefs, or we can even say that we want to make them politically correct. In other words, fairness is a concept which focuses on bias detection and mitigation in order to achieve outcomes fair in the understanding of the user. Before we can move on to the idea of FairPAN, I have to introduce you to the concept of GANs, which stands for Generative Adversarial Networks. It is important to understand that because our solution is strongly inspired by the behavior of GANs. Generative adversarial networks are two neural networks that learn together. The generator has to generate new samples that are indistinguishable from original data, and the adversarial has to distinguish if the observation is original or generated. The generator is punished whenever the adversarial makes the correct prediction. After this zero-sum game, the generator eventually learns how to make indistinguishable predictions, and adversary's accuracy drops down to 50% when a model cannot distinguish the two classes, which indicates that generated fake data is almost the same as the real one. Well, now, as we finally know what fairness and GANs are, I can tell you more about FairPAN. FairPANs are our solution to bring fairness into neural networks. We mimic the idea of GANs by subsetting generator with classifier, and the adversarial has to predict the sensitive value only from the output of the predictor, which is a vector of probabilities. Similarly to GANs, this zero-sum game is continued to the point when the adversarial cannot distinguish between two sensitive classes. In other words, it leads to the moment where information about sensitive value is greatly diminished or even lost. And it means that our model makes fair predictions. The crucial part of this model is the metric that we use to engage the two networks into a zero-sum game, which is captured in the following up function. So the model learns to minimize its prediction loss while maximizing that of the adversarial due to lambda being positive, and minimizing a negated loss is the same as maximizing it. The objective during the game is simpler for the adversarial because it only has to predict sensitive value based on the classifier's output, and this one is captured here. The adversarial doesn't care about the prediction accuracy of the classifier. It is only concerned with minimizing its own prediction losses. So during the whole process, it tries to get better at classifying the sensitive value. Now I'd like to describe the training process shortly. Firstly, we pre-train the classifier and adversarial on a balanced dataset. Unfortunately, we need to have similar amount of privileged and discriminated observations for the adversarial to work. After all, it makes class predictions based on vector of probabilities only. Later, we begin the proper PAN training with both networks. We train the adversarial, provides its loss to the classifier, and after that we train the classifier on a single random minimatch. We repeat this process desirable amount of times, and after that we should get predictions which are indeed fair. At this point, you might have asked yourselves really important questions. Why do we want to use such complex mitigation technique rather than use some other well-known methods? Or why do we even want to use FairPAN package at all? Well, regular mitigation techniques tend to worsen performance of the classifier by decreasing accuracy, for example, whereas FairPAN has no such drawbacks and worsening of the performance is much smaller. Moreover, the package itself is very flexible because it enables not only to provide your own neural networks, but also to create one with our functions. The outcomes are also created with the usage of DALEC and FAIR models, so one can use their methods and visualizations. Additionally, the workflow of the package is really simple and clean because of multiple features available for users, such as preprocess function. At this point, I'd like to introduce you to some graphical examples of how FairPAN works, which includes the knowledge about some metrics used to measure fairness. The example I'm going to use comes from the adult dataset, where the classification task is to guess whether a person earns more or less than 50,000 per year. Presented visualization comes from the package FAIR models written by Jacob Ruczyński, and it represents 5 metrics which are most interesting for the creator. And I can agree with this set of metrics because they are able to give us enough intuition about what is really happening in our data. On this plot, we actually see the ratios between discriminated group of females to privileged group of men in aforementioned metrics. We assume that the model is fair according to the particular metric when it satisfies the 4/5 rule. This 4/5 rule is satisfied when both labels in a sensitive class get similar results, which is between 4/5 and 5/4. On the plot, it is visualized as a green background color between the red ones. Now, as we know how to read such plots, I want to underline that the most important metric for us is the statistical parity ratio, called STP shortly. It is so valuable because it describes the similarity between distributions of our sensitive variables. As you can see, after the pre-train stage, our model is performing quite poorly in terms of fairness because its STP ratio equals only 0.3 and the other metrics behave poorly either. To check if our model works properly, we've decided to track the 4 most important learning metrics, which are loss and accuracy of the adversarial model, accuracy of the classifier, and of course, STP ratio itself. These statistics indicate if the model is learning well and makes desirable progress. As you can see, adversarial's loss function grows and its accuracy diminishes, which means that adversarial is worse with every iteration, despite learning to be better with every iteration also. We can also say that the classifier makes fairer predictions because the adversary can say which label is which. Last but not least, STP ratio also grows toward the 0.8–1.25 range, which directly means that predictions are fairer. As you can see from the last plot, accuracy of the classifier diminishes with every epoch. However, this loss is really small, and after all, we gain much fairer predictions while sacrificing only 2% of accuracy. Last visualization presents us the comparison between pre-trained classifier and final FairPAN model. As you can see, we've got almost perfect score for STP ratio. However, it didn't come to us at no cost. 2 metrics, equal opportunity ratio and predictive equality ratio, have drastically worsened their own scores, but it can be easily explained. The adult dataset is heavily biased, and what we actually done during fair training process was generating more true and false positives for female class in order to make the distribution similar. These changes, however, make other metrics change too, and it is clearly visible on the display plot. It shouldn't be feared, however, because the similarity of distributions is more important for us. In the end, I'd like to present you to the structure of the package and say a few words about using it. First thing that I will repeat a couple of times is that FairPAN is really flexible. Inside the workflow, we have many opportunities to provide our own methods instead of relying on the ones implemented inside the package. First example of this we encounter at the very beginning of our workflow. Although FairPAN data preprocessing is strongly recommended to use because it generates all new datasets, this step is skippable and one can provide data preprocessed by themselves. After that, we have to use a dataset loader function which creates batches which are needed in the further creation of neural networks. The next step is the model creation, which is also highly flexible. The user can decide to create both models from the package methods and pre-train them right after the creation. However, it is also possible to create them manually and provide them at this step. One can also decide whether the model given are pre-trained or not and provide the combination of models being pre-trained or not, which are visible on the graph on the right side. As a next step, one has to pre-train the networks if they are not pre-trained yet, and we can move to the actual fair training function. At this point, the user has to tune training parameters, such as number of epochs. It is also possible to choose whether models should acquire learning process statistics and if it should print them out. If we choose to save those stats, in the next step, we can plot them and see if our model works well and achieve desirable results. After the fair train, we can also decide to use explain_pan function, which creates dialect explainer on which we are able to use all dialect functions. We can achieve the same with fair models fairness check, where we create fairness object and it can be used in various models functions. And most importantly, we can plot the fairness check plot. To sum up, FairPAN is a competitive bias mitigation technique thanks to its low performance losses, applicability to neural networks, and achieving great results. It is based on the concept of GANs and efficiently uses it. Moreover, it is followed by an implementation of our package that is really flexible and easy to use. I can also recommend a few articles and blogs for further research according to this topic. The first article is written by my mentor, Jacob, and head of MI2 Data Lab, Przemysław Biecek. It describes Fair Models package and contains lots of information about fairness. Second one describes the idea of GANs briefly. Next two are blogs by Stijn Tonks and Han Griffin these two actually implemented the concept of FairPAN before me in their Python scripts, and I were deeply inspired by their work. And the last article describes FairPAN concept from the other perspective. So thank you for your attention, and I'd like to encourage you to ask some questions about my work.
Thank you so much, Hubert, for this great presentation. So very valuable resource study, and thanks a lot for your presentation. And unfortunately, we are already over. So yeah, we need to unfortunately stop for now. But so please, dear audience, don't hesitate to reach out to Hubert if you have any further questions. And thank you, Hubert, once again. And and then see you around. So, dear audience, we will continue with the community talk, and then have a good evening, and then enjoy the rest of the conference. Bye-bye.
Surely. Goodbye.